Okay, hey folks. A couple of announcements today. As always, there are always announcements. Homework 10 is due next Tuesday. Project 5 is due next Friday, and so a week from tomorrow. And then, once again, the course evaluations are live, right? So you can fill out your course evaluations. You can tell us all of the thoughts that you have about how we're doing the course. Currently, our response rate is slightly lower than we would like. It's 3%. The target response rate is 100%, so we have a bit of work to do to get that up. So please fill out the course evaluations as soon as you are able to do so. And yeah, we look forward to hearing what you think about how we're doing. Today we're going to continue our discussion of reinforcement learning, and we're going to sort of expand on the algorithms that we developed last time. Just to sort of recap what we talked about last time, there's this idea of agency, this idea of like, okay, we want to design intelligent decision-making systems. Well, if they're going to be decision-making systems, they have to make some decisions. We have to put them in environments where they have to make decisions. And this feedback loop between the agent and its environment is key to the picture of what it means to be intelligent. So an agent will take actions, the environment will respond, we'll get some sort of updated environment state, and then we have to make decisions in that new state. And we have to set ourselves up not just to get immediate rewards, but to get long-term sort of future rewards, set ourselves up for success in the future. Because we want to maximize our long-term expected sum of rewards. Okay, so we talked about how we're still going to use the Markov decision process language. We're still going to use the formalism of MDPs. So we have all of our states and our actions and our transition function and reward function, and as before. The goal is still to find a policy. But now, instead of seeing these transition functions and these reward functions, the agent isn't going to see those things anymore, and it's going to have to just experience the world and figure out how the world works by interaction. So that's the picture. We talked about a few distinctions. This is sort of the fundamental difference between MDPs and RL, was this offline versus online, this planning versus learning setup, right? So in planning, you have this model of the world. You get to try things out in your head before you do them, much less dangerous that way. And in the learning setting, you just have to try it out and hope for the best. We also talked about passive versus active RL. And passive was when we had a fixed policy and we were just kind of trying to figure out how good is it doing. This is very much like policy evaluation, except, again, now we don't have the transition function, we don't have the reward function. All we have are samples from the environment that are telling us how that policy was doing, what states was it reaching, those kind of things. Versus active reinforcement learning, where the agent is like the one who's in control, and it's evaluating how it's doing on its itself. So it can decide, you know, hey, I jumped into the pit of fire, I got a big negative reward, maybe I shouldn't do that again. So you can kind of learn and update your policy on the go. So passive versus active, fixed pi versus changing pi. And we talked about a few different approaches to reinforcement learning. One was the sort of most straightforward approach. We wish we had this MDP model. Let's just learn an MDP model and then solve that MDP model and take the policy that comes out. And then we said, okay, well, there's a few problems with model-based RL. Maybe we can try to learn how to act in a model-free way. And we looked at this sort of idea of direct evaluation, where we look at a big batch of experiences. We see which of those experiences started in a particular state that we're estimating value for. And we collect all the experiences that started in that state, and we see what were all of the long-term expected discounted rewards from those states, and we just take an average. This is just sort of like the direct evaluation, direct estimation approach. And last time, so we were doing this, we did this, and then we did this part. And so we were sort of looking at this temporal difference learning piece as like a potential way that we could fix some of the problems with direct estimation. Remember, there were like, we could learn things about certain states. We had that sort of like cross-shaped grid world. It looked like, it looked like this, right? And we said, okay, so this is the model-based setting where we learn T and R, and then there was the direct estimation setting where we said that there was this problem, right? We had two states that both definitely led to the C state, but but for whatever reason, whatever we learned about C couldn't be propagated back to both B and E in a satisfying way. We had to sort of estimate B independently of everything else, and then estimate E independently of everything else. And it would be nice if we could kind of get some savings, because that computational win would be helpful when we're trying to train things efficiently. Okay, so kind of diving back into this idea of temporal difference learning, we said, all right, well, let's start by expanding this Expectimax tree. And let's think about what we would be doing if we were trying to estimate the value of a state. We've done this before with MDPs, so it's very similar. And in the MDP case, we can just write down the Bellman equation. We say the value of a state is equal to this expectation over the transition dynamics of the immediate rewards plus the gamma discounted next state value, right? So we start by looking at the value of a particular state, right? This state. We say, okay, well, there's a fixed policy, so we don't have to take a max over actions. We just take the action that the policy tells us to take. And now we have this chance node. Normally, we would look at all of these actions. We would sort of multiply the probability of each action times the value that our value function is estimating for each of those states, and we'd be on our way. That would be our expectation. But we also talked about another way that we can estimate expectations last time, which is just taking the sample mean, right? If I have a bunch of people who I want to know their average age, I just ask everyone what their age is, and I divide by the number of people. So there were a few modifications that we wanted to make to the classic Bellman approach in order to make this work in reinforcement learning. The first modification was, of course, we don't know T and we don't know R, so we can't just write this down like we did before. Now we will have to estimate from samples. So we go and experience some transitions in this environment. We gather some, state, action, next state, reward tuples together. We add them, we put them all into a list. Maybe we get n of them. And for each one of those, we calculate R plus gamma V of S prime. Whatever V of S prime our value function estimate is currently telling us. It doesn't have to be the correct value function, but hopefully as we update V, it will get more and more correct over time. Okay, so then I started to talk about two modifications, which I'll sort of group together into one and just say, we're going to try and update V after every transition. And we're going to use this concept that I introduced at the very end last time, which was this notion of a running average. How can we keep this estimate of a sample mean and update it in constant time as new data comes in? And there's one more modification that we'll have to make, which is to decay older samples as new ones come in. And I will claim that the algorithm that I'll present now will do both of those things, and then we'll sort of like look at it afterwards and see if it actually makes sense. So let's do an example with TD value estimation. The first step is we're going to experience a transition. We'll call this transition I. So this is going to be a state, action, next state, reward tuple. Okay? So we just write it down, SAS prime R. Okay? And then we're going to need to compute the sampled value target. This is kind of where we would like our value function to move towards. That's why it's called a target. But this is one of the samples in our sample mean, essentially. Okay, so this is our R plus gamma V of S prime. We just say, if I was in this state, the Bellman equation tells me that this R plus gamma V of S prime should, in expectation, be equal to the value function at the current state. So let's calculate what it is for this transition and see how close it matches. Okay, so we can actually compute a TD error. This is the time difference, the temporal difference error between what we thought the value was going to be and what the sampled value actually was when we sort of let time unfold for one step. So we take our R, we add that to gamma times V of S prime, and we subtract off our initial value estimate. So if I'm in some state and I take one step to the left and I think, ooh, I was expecting to get more value, but I stepped to the left and I didn't get any value at all. Then I have sort of like a TD error, and then I would write that TD error down like this delta. Okay, and then the last step is that we're going to update the value by adding some sort of multiple of this TD error. Basically, if the TD error is positive, it means that this first piece, the actual experienced value, was bigger than this second piece. Meaning, we thought we weren't going to do we thought we weren't going to do as well as we did. We surprised ourselves, and it was kind of a delightful surprise, right? We were sitting there, we're thinking, this state's not that good. Let's take an action. Probably won't be that good. And we take the action. Oh, wow, that was actually really good. Okay, so this is like a nice little surprise. And so this is saying that we have a positive TD error. This is saying we're doing better than we expected. So then we should increase the value in the state that we started from so that we will be expecting to do better in the future. And similarly, if we start in that state and we think we're going to do great, and it turns out, we don't do that great, and we move over here, and it's worse than we expected, well, we had better go back to that state we started in and decrease our value estimate. So that's what this TD error is doing, and we're going to update V proportional to this TD error. Yes? How do we decide which action to take? So for TD, we're just going to say we take whatever action the policy tells us. And then we will relax that in a moment. Yes? So yeah, which one of these is the estimate? So this one here is the estimate. This is like how much value do we expect to get from state S? And then we go and try out the action that the policy told us to take, and we say, well, what value did I actually get? Well, first I got this reward, and then I'm still going to use my estimate of whatever comes next. This is like I've unrolled my search tree by one step. So we start in state S, and then we take the action pi of S, and that brings us to sort of like this node, this Q state, S pi of S. Sorry, having trouble writing. And then all of these states are what we would sort of normally think of as like the chance node outcomes. But we're going to sample from this chance node, and we're going to get one of those. And let's say we get this one. That takes us to an S prime. And so the actual transition that we observed was S, whatever A the policy tells us, S prime, and then there's some R associated with that. So this is like, what did we experience? And then we're going to use our value estimate, V of S prime. This is still an estimate. So the distinction is a little fuzzy because we're using our estimate to compute a sort of sample of where we would like our estimate to move towards. It's a recursive thing. Does that answer the question? Great. Yes, other question. Is this part of the exploration or exploitation stage? Well, I guess I would say it can be useful for either, but it's not necessarily one of those two things specifically. So what we're doing right now is we're saying, how am I doing? How am I doing with this policy? We're trying to estimate the value of the policy. So this isn't like we're trying to maximize, right? Because we're not changing the policy. So we're not really exploiting in any sense, unless we were doing that before. So this is sort of like in between exploration and exploitation steps. This is like, let's just make sure that I understand what it is that I'm doing so that the next time I explore or the next time I exploit, I have a better sense of what to do. Thanks for that question. Other questions? Okay. Right, so the basic idea is we're going to use this TD error to update our value in the direction that would have minimized this TD error so that in the future we won't be making these kinds of value mistakes. Okay, so let's see how that works. We go back to our sort of cross-grid world. We observe some episodes, and we want to sort of write down what the output values are. And I'm going to go through this example in a slightly different way than before, just because I want to have the algorithm in front of us while we're doing it. So we'll write those episodes on the right, and here's the algorithm again. And we'll write down a sort of value function table on the left, And then this is sort of like a workspace to keep track of everything, because there's a lot of quantities to keep track of here. All right, so let's go through. We're going to go through these experiences like this. So we first get this experience. We haven't even finished the first episode yet. So in our minds, like these are the experiences that are coming, but like we're going to have to update the value function after every single one of these experiences. So right now we've only seen one experience. We were in state B. We went east. Maybe I'll draw this thing again. Right? So we're in state B. This is C. This is D. This was E, and this was A. Okay? So we're in state B. We go east. We see state C, and we get a -1 reward. All right, so we can fill these things in. B, east, C, -1. We should probably initialize our value function to something so that we can calculate these next few pieces. So let's just initialize it to all zeros. That's like the classic thing we do. Okay, so we started in state B. So what was our value function for the starting state? Well, it was 0. We just initialized it. We haven't updated it yet. And what does experiencing this transition tell us was the value of being in that particular state? Well, it's R plus gamma V of S prime. The R, we just wrote it down, is a -1. And the V of S prime is still 0. So we can say -1 plus 0. Okay? So subtracting this target, this is the target here. This is our sample, the thing that we're going to be using to update our value. So subtracting target minus our initial value estimate, we get -1. Okay? So things are worse than we expected. We thought we were going to get 0 value, but we actually got -1 value. It's even worse than we hoped. Okay, so now we have to update the value of the state we started from, which is B. So we go into our value function table, and I'll write it in blue. We make this update. It's, it's -1, the thing that we just calculated. This right here. Okay, so we have to, and we'll just say that this alpha is 1 for the sake of making the math easy for us, right? So we update the whole thing. We get rid of all the TD error in one step. Okay, next sample. Everyone see how we did the first sample? Questions so far? Okay, nice. Let's look at the next sample. So the next sample says we're going to be in state C. We're going to go east to D, and we'll get a -1. So we're in state C. We go east. We go to D, -1. So the reward is -1 again. And then we can look at our value estimate for the next state. What's the next state? It's D. Well, everything besides state B has a value of 0. So we just add our 0 in there. And what did we expect for state C? We just look in this table. It's still here. It's 0. Right? So same situation. We get a -1. And then we can go and update the value of state C, which is the state we came from, to minimize this TD error. So we put a -1 in there as well. So normally when you would go through this, you would have some alpha, which would like control how much of an update you take. That's called the learning rate. But right now we're just going to say alpha equals 1 to make the math easy. Okay, so let's look at one more sample. We have D. We take the exit action. There is no next state because it's a terminal state, so we leave the MDP. And we get a +10. So we get a +10 here. And then what value do we use? Well, there is no next state. So when there's no next state, there's nothing to add, right? So it's just the reward. So regardless of what our value estimate was for D, we would just not add it because we're not reaching an S prime here. So that's like a kind of subtle bug, and this has like tripped up lots of people in the reinforcement learning field. So don't add the value of the next state when you reach a terminal state because there is no next state. Okay, but what are we comparing this with? Well, the value of being in this starting state. So D, the value of D is still 0. So then this is a +10 for our TD error. So we go over here, and I'll just write it right on top because that's a 0. So we add 10 to our value for D. And that's the end of the first episode. So we've gotten to here. Okay, so that's 3 experiences. Make sense? Should we keep going? Okay, let's keep going. So, meaning, should we keep going with more of this, or should we move on? Who wants to see more of this? Okay, nice. All right, good, because I also want to do more of this. B goes east to C. We get a -1. So we have a -1 here. That's our immediate reward. Plus, what's the value of the next state? Yeah, so we're seeing C again. And so now we have to add the -1 from our value function here, right? So we have this. We have to add that in. So now we have -2 is our sort of sample target. And what's the value we started with? Well, now C is -1, right? Just look at the value function. So our estimate is getting lower and lower. And now our TD error is the same as before. It's -1. But so we actually have to go in and update this entry in our table to be -2, right? So -1 minus another 1, okay? And that comes from here and here. So -1 minus 1 is 2, okay? So we've now done this sample. We can cross that off the list. So let's do another. So now we have C goes east to D. Okay, we get a -1, so that's -1. We have a value. What's the value of D? 10. So we add 10, right? This would normally be gamma discounted, but we're trying to make the math easy on ourselves. So, and what's the value we predicted? We predicted 10. Sorry. Yeah, we predicted -2, right? So the value of C. Okay, so what's the difference? The difference here is this says 9, this says -2. So our difference is 7. Great. Okay, so what do? We add 7 to our -2. Say again? Can't hear you. It should be 11. Did I make a mistake? Right, so we had our -1 plus our 10 for going to state D. That's 9. So we have 9 minus -2. I see, yeah. Okay, good point. Okay, 9 minus -2. That's 11. Great. Okay. So we have to add 11 to our -2, and that gives us C equals 9. And we'll start writing in another color now. Okay? So that came from here and here. So C equals 9. Yes, question?
I think you updated C twice in a row. Is that...
Okay. So maybe I made a mistake here. So let's see. It was minus... Does anyone remember where it was when we started? Yeah, okay. So if it was -1 when we started, we can do this. Let's clear this out. We say it started as -1. So we want to go C goes east to D. We get a -1. So we have a -1, and then we have to add the value of D, which we said was now 10. This equals 9. And then our initial estimate was -1. So our delta is 9 minus -1, which is 10. Okay? Okay, so maybe I'm making a mistake. Maybe it was starting as -2. Yes?
I think it should be B that's -2. In step 4, that was like our initial state.
Okay.
And C
C
is still -1, but B is -2.
is still -1, but B is -2. Okay. I think you might be right about that. Let me ask this. Who is confused on the process? And maybe I'm just messing up the math a little bit. Raise your hand if I need to explain the process better. Do you see what we're supposed to be doing here? Question.
Do you update the node you're going
you want to update the node that you're coming from. So let's say that I'm in state, whoops, we're in state B, right? Oh my goodness. Struggle with the slides today. All right, so we're in state B, right? We move to state C. We want to update the value of state B. You always want to update the value of the state you're going from. And you can think about this in terms of like when you have a terminal state, there is no state that you're moving to, but you still want to make an update. So you have to update the state that you're coming from. There's always a state you're coming from. Question? Yeah, okay, so now I see the confusion. Yes, this is a mistake. This is just S. Great, good question. Yep, sorry about that. So we're updating the value of the state we're coming from, which is S. Yeah, sorry for that. That was my mistake there. Okay, so V of S gets updated according to this difference between unrolling the sort of transition by one step, and this should also be V of S. So this is where did we think we were starting from? Okay, I will clean those up and then we'll post the updated slides. So yeah, sorry if that was confusing. Okay, more questions on the process? Sorry for making a bit of a mess there. Okay. So let's see where we get to. All right, so we'll fill in the table, and the table will tell us which of these things were correct. The table now looks like this. Okay, so some of these were correct, some of these were not. It will turn out that after you do all of this stuff, let's look at this last row. So what happens here is that E moves north to C. Right, so we're sort of like crossing this grid again, right? We had this situation, E, C, and B. And remember we said we wanted it to be the case that when we learn the value of C, we can use it in both B and in E, right? We want to reuse this computation. And that's exactly what's happening in this last row of our table. So E is moving north to C. And at this point, our value estimate at C is 9. So we learned that it was 9 in sort of the process that I was fumbling with down here. So we got an updated estimate of C, and now when we get to E, we can use that estimate to build a better sample, right? A better sample target. We learn the value of E faster because we use the episodes that don't even touch E, but that do go through this common middle state, C, to our advantage. We don't have to redo the computation. So does everyone see how this is going to like save us some computational cost here? We get to reuse the stuff we computed in C when we get to E. So that's really nice. So you run this for a long enough time, and eventually you get a +4 here. This is the same as before, but now instead of having sort of two different values at B and E, they're both going to have this sort of one-step removed value, and so everything's going to kind of be nice and symmetric, and we're going to be happy about this. Okay? So that's temporal difference value estimation. It says we have an input policy. We want to know, basically we would like to do policy evaluation to see how good a policy that is, but we can't do policy evaluation because we can't just unroll this expectimax tree like we normally could. We have to do this sort of sample mean thing, and we wanted to do it. I said that we would do these two pieces. We were gonna estimate we were gonna update the value of V of S after each transition, and we were going to use a running average, and we were going to decay older samples as new ones came in. So let me try and prove to you that we're doing those two things. So we talked about running averages last time, right? So if you want to compute the average of a bunch of numbers, you could always just add them all up and divide by n. But if you have a longer sequence, you don't want to have to add them all up again, right? If I had a sequence that now had like a 5 on the end of it, right? I don't have to add 5 numbers. I already added 3 numbers. I'm not feeling like I have that kind of energy today, right? So I already added 3 numbers. I can't add 4 more numbers. I want to add 1 more number. So we talked about this last time. There's 2 ways you can do this. One is to keep track of a running sum and keep track of a running count. Basically, the running sum says, what's the total of all the numbers I saw so far? The running count says, how many numbers did I see so far? You can update both of those in constant time. We showed how to do this last time. And you just divide one by the other. You have your new estimate of the mean. That's how you take a running mean, running average. An alternative way is you could keep a running mean and just multiply that by your current count right before you have to do computation. So this running mean estimate, here's the algorithm for it. You take your sum at time step n minus 1. You add the nth data point to that. That's your new sum. You divide by the new count. Or you take your old mean, you multiply that by n minus 1. That's essentially the same thing. That's computing the sum. And then you add your new data point and you divide by n. Okay, so we can do that for this example. We start with both of these things initialized to 0. Then when n equals 1, we have to take our 1 sample and divide by 1. Pretty easy. The first number is 1 anyway, so we have 1. The second sample is a 4. So we have to add that to our running count. We get a 5. We divide by 2. It's 2.5. We do this for the third one. We add 7. 7 plus 5 is 12. Divide by 3 is 4. An alternate formula for this is you can sort of rearrange some terms, and hopefully you should be able to convince yourselves that this is the same thing. It's really just a weighted average of the old mean and the new sample. A weighted average. The weights are n minus 1 over n and 1 over n. So stare at these weights for a second. What's going to happen as we get more and more samples? How much weight are we going to give to the newest samples? It's going to go down over time, right? So that makes sense, because as we get a better and better estimate of the mean, we don't need as much information from these new samples. So we're going to kind of get more and more stable estimates over time. But that's not what I showed you in the previous slides. In the algorithm, it was more like this kind of situation. We had this 1 minus alpha and an alpha term multiplying the new estimate, the new sample coming in. So what would it be like if we had like a fixed weight, right? Rather than this decaying weight, this weight that started with that was 1 over n for each new sample. Well, we go through and we take this 1 over alpha, and we're going to multiply that through. So right, the first sample is easy. The mean is just the first sample. But the second sample, we plug in this formula. We have 1 over alpha times our existing mean, which is x1. We can plug this in here. So x1, I'll write it in an easier to read color. Okay, x1 goes there. So that's 1 minus alpha times x1 plus alpha times x2. Let's look at the next one. So in the next step, we have n equals 3, and now we have, let's expand, right? The mean at step 3 is 1 minus alpha times mu2. What's mu2? Well, we just calculated it. It's 1 minus alpha times x1 plus alpha times x2. So we plug that in. We get 1 minus alpha squared times x1 plus alpha times 1 minus alpha times x2. And then we have to add this remaining piece, which is the alpha times x3. And we can go one more step. It's going to be 1 minus alpha cubed. So we can see that as n gets larger, we are multiplying the first term by 1 minus alpha to the n minus 1. So this is basically saying we're going to exponentially forget old values. So as time goes on, we're going to forget what we saw early in the training process and mostly focus on these sort of newer values. Now, why would we want to do that? That's what this algorithm is telling us we're going to be doing. Why would we want to do that? Well, if we go back to this table, right, it took us some effort to get through this table, but what we noticed was that these had like really bad value estimates, right? There was always a TD error at the beginning. It wasn't until here that we got our first our first sample that didn't even have a TD error, right? So these are bad value estimates. So we shouldn't give them so much weight in our weighted sum, right? We should actually, over time, we should try to reduce the contribution in our average of these estimates, because we were using our estimate, which we knew was bad, to produce our new estimate. Sort of it's hard to wrap your head around why this would make sense, but as long as you decay these older samples, the newer ones will eventually get better and better, and over time your estimate is still going to converge to the right thing. Does that concept make sense? So we're exponentially decaying these values. Okay, exponentially forgetting them. And you might want to stare at this and see, is this still going to work? But because now we have, how I'm reweighting the samples. How do I know that this is going to still converge to the same expectation, right? But it turns out that any weighted combination of samples, as long as those samples are identically distributed and independent from each other, it will still converge to the same expectation, right? If I put it this way, if I ask 100 people what age they are, then I'm going to get some estimate of the average age when I divide by n. But if I just ask the last 50 of them what their average age is, it might be a little noisier because there won't be as many people in my sample, but the expectation of those random variables is still the same thing. There's still some underlying random variable whose expectation I'm estimating. And this is a very similar concept. It's saying, we can change those weights, but as long as all the samples are independent, we'll be good to go. Okay? So we experience a transition. We compute, we'll have to update these slides. This one is correct. We compute the sampled value target. This is where we'd like to move our value function to. We would like to move it from v of s towards this new target, so we calculate this temporal difference. And then we want to update with this TD learning rule the value of some state s with its current value plus this delta, plus alpha times this delta. And this alpha is multiplied by this target minus, see here I got it right. So v of s is v of s plus alpha times target minus v of s. And we can rearrange that to be v of s gets 1 minus alpha times its current value plus alpha times its target value. So we have this weighted combination. And that's going to get us that exponential decay. So this alpha term is what's called the learning rate. Sometimes it's called the step size. It's saying how much should we move in the direction of the target. So we observe a sample. We move v of s a little bit to make it more consistent with its neighbor v of s prime in this one-step unrolled version. This is also called bootstrapping because we have this value estimate that we want to get more accurate value estimates, and we're using our current value estimate to build ourselves a better value estimate. So this is why it's called bootstrapping. We're starting with a bad estimate and trying to use it to get a better estimate. Okay, so this is a cool algorithm. It works pretty well, and it also happens to be something that they've discovered happens in the brain. There are sort of neural signals in the brain. The neurons transmit this dopamine to encode reward or value prediction error. So basically, when there's a stimulus, right, a reward happens here. If that's sort of a surprise and we weren't expecting to get a reward, we get all of this sort of dopamine released in the sort of time step right after that. And this encodes this TD error signal. So it strengthens the neural connections that would then predict that in the future. Meanwhile, if we don't see a reward, right, there's nothing there to see, then we don't see this extra dopamine showing up, and we're not going to strengthen those neural connections. And similarly, if we were expecting a reward, if we're expecting to see a reward, and then we don't see one, then we get a negative dopamine response. So what this is saying is like things are worse than we expected, and so we will weaken those connections and we'll sort of strengthen the opposite connections. So this is cool. It's an example of like neuroscience and AI sort of informing each other, because the TD learning rule originated in AI, and then they went back into neuroscience and found that it was happening. So that's super cool. Okay, so a few problems with TD learning. Okay, on the plus side, it helps us do model-free policy evaluation. That's great. Hooray. It helps us do these Bellman updates without or with a running sample mean. So that's kind of fancy, and it means we don't have to compute these things with models. Take a look at this search tree, though. Like, what if we wanted to do policy improvement? What are we computing? We're computing the value of a state, S. We're computing the values of these states, these S primes. So how do we choose an action? Well, normally we would say take the max, right? Take the max over the actions of, whatever the value of that action is, sort of like the Q value of S comma A. You can expand that. You could say like a Q value is just a sum over, what's going to happen down here. Those would be like transition dynamics. But here's the thing. We don't have the transition function. So we can't multiply that by this R plus gamma V of S prime. Right? How are we going to do this expectimax thing? How are we going to choose our max over actions? So TD doesn't help us do that. That's super unsatisfying, right? We need the transition model still to improve the policy. Oh no! What are we going to do? Well, what information would help us to take this max over actions? Well, if we knew Q, right? If we had estimated the value of these things, these Q states, these SA pairs, then we could just take a max. It's, look at A things and then take the best one, right? So if we had estimated these Q values instead of these V values, we would be golden, right? Okay, so that's going to motivate the next algorithm, which is called Q learning, and we'll take a quick detour and think about Q value iteration. So in value iteration, right, we're sort of like, we're starting with some value function V, which we know is correct because it's only looking at the sort of one step or the 0 step value. And then we're going to calculate VK, which is like a depth K search for all of the states. And the update looked like this, right? We said the VK value function for a given state is we take this max over this transition function of our rewards. This should be a boring equation to you by now because you've seen it so many times. But Q values are way more useful, right? So we should just maybe compute those instead. So we'll start with a Q value table. It'll be 0 for all state action pairs. And that'll be right because we'll only look for like one step in the future. And then we're going to try to compute Q sub K in this recursive fashion, right? So we'll say Q sub K of SA is whatever the transition function says is likely to happen, plus times the reward for that transition times the gamma discounted max over the next state Q values. So now we can write, because this V we looked at, this is like a max in our search, right? So if this is a max over actions, we have a max over these Q states. So V is up here and these are Q states. So what we're doing is we're replacing this V with this max A over Q. And now we can write this Bellman equation in terms of Q values instead of V values. So that's the basic idea. Everyone see the switch we made there? It's the same Bellman equation, it's just in terms of Q. So we've moved one half of a step down the search tree. Instead of starting at V, we're starting at Q. And then we're going down in our expectimax search to these next V nodes, right? And then we're going down to the next Q nodes. So we're looking at this block. sort of a messy diagram. Does it make sense? Great. So Q-learning is just going to be approximate Q iteration in the same way that TD learning is sort of like approximate value or policy evaluation. Right? So here's the definition of Q values. Q is the expected return for committing to doing action A, no takebacks, from state S, and then behaving optimally thereafter. And the optimal policy, pi star of S, is defined as the maximum over, this should be an argmax, saying which action would maximize the Q value in that state. Okay? So we have this Bellman equation for Q values. We have Q star of SA is equal to this thing. And it's written in terms of Q star of S prime A prime. So this kind of has the same recursive structure as before. And we're going to approximate this Bellman equation for Q star with an approximate Bellman update for Q values, right? So we have some estimate Q of SA, and we're saying we would like to move that same as we just did, right? We want to start with some weighted combination of Q of SA and whatever this target value is when we run it through one transition in the environment. So we have an R plus a gamma times a max over actions of our next state Q values. So we look at all the A primes we could take when we get to state S prime. We say, okay, this one's the best. We're going to use that to bootstrap. We have this R plus gamma of this max of A's of Q of S prime, A prime. That's our Q target. This thing here is our Q target. And we want to say, let's move Q in the direction of our Q target. That's why we call it our target. We'd like to move there. Okay, and alpha is still the same learning rate as before. And what this will allow us to do is then we go back, once we get a good estimate of Q, once this thing has converged, we can then take the argmax over Q values, very simple, and then we can pick our optimal policy right by looking at the Q table and picking the maximum action, the argmax. Right? So we obtain a policy from the learned QSA with no model at all. We learn a value function with no model. We then compute a policy with no model. Okay? Amazing. We did it. Reinforcement learning. There is one caveat here, which is that the Q table is going to be A times larger than the V table. So if you have lots and lots of actions, or if you have infinite actions, this might be tricky to write down. So there's no free lunch here, but like typically if you have a finite number of actions, and hopefully that number of actions is small, this is like a reasonable thing to do. People do this all the time in practice. Okay, let's see them doing it in practice. So let's learn the QSA values as we go, and we can do this for the grid world, this 3x4 grid world. And what you see is that like this will ultimately converge to reasonable looking Q values. So yeah, so like if you just look at this state, it's saying that the optimal policy from this cliff edge state is to go left. And we initially thought that didn't make sense, but like it makes sense when you can consider that this thing is learning about slip probabilities. It's experiencing the environment. It's learning that, you know, every time I went north, I got a minus 0.51 on average. Hopefully people can see the numbers, but if we go north, we might slip into the fire pit, right? But the way that the slip probabilities work, we never saw experiences where we try and go in one direction and we actually go backwards. So if we walk into the wall, after a little while we might slip out and move up, or we might move down. And so that's the best action to take, is to walk into the wall. Right? So we receive our sample, we consider our old estimate, Q of SA. We consider our new sample estimate. This is our Q target. This is R plus gamma of the max over SA primes, S prime, A primes. And then we incorporate the new estimate into our running average by doing this weighted update. Okay? So very similar to TD in the same sense that like policy evaluation and value iteration and policy iteration. Those all have similar looking Bellman equations. Now we have two similar looking update rules. But TD is for a fixed policy. This is like the passive learning case, where we're just watching our video of what this agent was doing. We can't change the policy at all. And now Q-learning is saying we can actually change the policy if we want. We can go in and we can, once we take an update, we can improve our Q estimate, and then we can, be greedy with respect to that Q estimate and then change our policy. So here's what that would look like in a grid world. I think this is a slightly different grid world. So this grid world, the way that this works is, I'll draw the fire. There's fire all down here. Don't go down here. It's all fire. Okay, so we're on a cliff edge. So there's a nice terminal state over here that we would like to reach, and then the rest of these states we can sort of move between them. But if we jump off, we'll fall into this pit of fire and be sad. Right? So let's keep the video going. That's how it works. So yeah, so we run through one episode, and let's say that we're just controlling it so that we can move it towards that green state. Okay, we learned the value of the green state. Hooray. All right, so let's do this a bunch more times. Let's just keep moving towards the green state. And you can see we're starting to propagate this Q value backwards through our MDP. Right? So our Q table is getting sort of more and more green. If we just keep running into that state, slowly these values are trickling back. At some point we actually jumped off, right? So in this one, I think this episode we jumped off just for fun, to see. And we landed in the fire. We didn't know that was fire yet, so totally reasonable thing to do, but we found, oh, that's not that good, right? So I don't know why we're doing it again. This is someone else controlling the policy. So, okay, we jump off. Notice that no matter how many times we jump off, they just jumped off like 3 times. The Q value of these states that lead up to that state, right? The Q value is over here. Whoops. Oh, no. Notice that no matter how many times we jump off, the Q values for those first 3 states, these ones over here, they don't go down, right? Because the Q value is the max over the actions. It's saying if I first take this action and then I act optimally for every time step after that, then what's the value I should expect? And acting optimally means not jumping into the fire at that 4th square. So we don't think about, oh, what if someone jumps into the fire? It's like, no, they're not going to. They're going to act optimally for the rest of the episode. So it doesn't matter how many times we jump off, we can still improve our Q values for all of these other states. Okay, so let's let the video finish. We can also jump off from some of these other states. I think we do that. Maybe not. Yeah, we jump off from there. We see a few fire transitions, and again, we're not updating. So this is like Q-learning working. We're learning our value function, and here someone else was just controlling the policy. It actually turns out that Q-learning converges to an optimal policy even if the samples are generated from a suboptimal policy. As long as you explore enough, as long as you see every state action pair an infinite number of times, then you will explore enough and your values will eventually converge to Q star, this optimal Q value function. You do have to eventually make the learning rate small enough, but you also need to make sure you don't decrease it too quickly. So there's a few trade-offs here, but in the limit, it doesn't really matter how you select actions. And so this is sometimes called off-policy learning, because you can be learning about the value of those Q states, those SA pairs, without actually having to commit to a particular policy. So that's why it was okay that someone else was controlling the agent in that example. Q-learning doesn't mind. Q-learning will still get you reasonable Q values. Okay, but there is still this trade-off between exploration and exploitation. We saw this cropping up in the Bandit lecture. And it says, we should balance trying new things with doing what's best given what we've learned so far, right? So the same principle applies here. pure exploitation often gets stuck in a rut, and it never finds an optimal policy. But as long as we're trying a bunch of new things, then we looked at this idea of like epsilon greedy, right? So with some small probability epsilon, we're just going to act randomly. Well, that's going to help us to see actions that we didn't necessarily see before, actions that weren't on our policy. We can go off of our policy to some extent. And then with large probability, we'll act on the current policy. Right, so properties of epsilon greedy is that every state action pair is tried infinitely often, but it does a lot of stupid things like jumping off a cliff many, many times just to make sure that it's like really as bad as we think that it is. So unless we decay this epsilon towards 0, it's going to keep doing stupid things forever. So what does decaying epsilon greedy look like? So here's the crawler example. So we start with some epsilon, and the mouse is kind of showing you the epsilon, which is currently reading 0.8. It's saying that we're taking actions randomly 80% of the time. Okay? That's quite a lot of random actions. It's just mostly doing crazy stuff. Right? So if we skip forwards, it's like still struggling to make some forward progress here. But eventually, we're still generating these transitions, and we're still updating our Q values, and we can update those Q values independent of whatever the policy is. So if we then go in and we crank down this epsilon, and we make it lower, which I think we'll do in 1 second, right? We crank epsilon down, so it's currently 0.8, and now we go down to 0. Okay? This agent will then start slowly moving its way across the floor. Like it learned from those transitions. It updated the optimal Q values despite not having an optimal policy. And then when we say, okay, just like decrease epsilon, it's funny that they show the slide in the video. So when we decrease epsilon, then we can start to exploit this Q value that we learned, right? Another option, and we talked about this in the bandits lecture as well, is we can make these exploration functions to implement this trade-off for us. So we can take a value estimate, and we can add a bonus when we see things that are things that are novel to us. So the bonus could scale. Basically, when we see more samples, we can decay this bonus. We start with some big bonus k, and then as n gets larger, we scale the bonus down as like the square root of n, 1 over the square root of n. So normally we would have this regular old Q update, which says r plus gamma max q s prime a prime. Now we're going to say, instead of just taking the Q value for granted, we're going to say add to that Q value some bonus, right? So we compute our optimistic utility by looking at this exploration function and seeing how much it's saying we should add. So this will actually propagate this exploration bonus back to states that lead to unknown states, in addition to states that lead to high value. So this is a nice way to trade it off too. Okay. So here's what adding an exploration function does to this crawler example. So here we have a small epsilon, it's 0.1, but we've added an exploration function, so there's this bonus for seeing new states, basically. And what you see is we don't even have to skip forwards. Slowly this thing is going to learn to crawl to the right, even though we didn't have to skip 30,000 steps or 1,000,000 steps forwards. It just starts crawling to the right because it's incentivized to reach new states. So there it goes. It's moving slow, but it's moving, right? Okay. Mesmerizing. All right, so now let's talk about approximate Q learning. Basically, what happens when there's too many states to write this table down? So basic Q learning keeps a table of all the Q values. And we said the Q table is even bigger than the V table, right? It's A times bigger. But usually A is not the big thing. Usually S is the big thing. Usually there's lots and lots of states and maybe a few actions. Think about this Atari video game, right? If we're playing Pac-Man, there's a small number of actions we can choose. There's up, down, left, right. That's it, right? So there's lots and lots of states, right? I could have a dot here, I could have a dot there, I could be in this position, that position, the ghosts can be all over the place. There's so many states. It's hard to even write down all the states. But we only have a small number of actions. So it's the states that are going to kill us here. Maybe we can, instead of keeping a Q table for all of the Q values, we can try to do something more succinct than that, right? Because we can't just go and visit every state. We can't try every action in every state. There's just too many actions and too many states, or too many states, and trying a few actions even in all of those states is going to be tough. So instead, we want to try and generalize. How can we make our experiences in one state generalize to experiences in other states? How can we see, whether states sort of look like each other so that we can make these sorts of generalizations? Let's suppose that we discover through experience that, and if you've played Pac-Man, this state is bad, right? We discover that through experience. We're a Q-learning agent. We find ourselves in this state. It doesn't typically lead to high reward. Okay, so in naive Q-learning, that state is completely different from this state, which looks pretty similar. So we know nothing about this state if we're just writing everything down in a table. But they do look kind of similar, right? What's similar about them? We're surrounded by ghosts. We're in the corner of the maze, right? And that first state is also completely different from this new state, where there's a missing dot in near the corner, right? So there's this dot is missing. See that missing dot? There's a dot over here. So these two states are completely different if we're just writing things down in a table. But that's kind of silly, right? We should be able to learn from one of these experiences that the other one is also bad. Okay? So how are we going to do that? I think I'll skip through these ones for time. Let's just watch this one. Okay, so we learned that that's a bad experience. We learned that's a bad experience. We're sort of like, okay, every time we hit a ghost, ghosts are bad. Okay, but all of these are different states. We don't really know how to handle these. What should we do? What should we do? We try our best, but we're not learning anything useful. At this point, the ghost does a victory lap. Right, so maybe we can try and generalize between states if we use this idea from machine learning, right? We have features of states, like, hey, I'm close to the ghosts. That seems like an important feature to pay attention to. I'm close to dots. Dots are good. I like dots. Right? So closest dot, the distance to the closest dot, distance to the closest ghost, number of ghosts. Are we in a tunnel? Lots of different things that we could write down as potential features for this environment. And we can also describe Q states with features. So it doesn't have to just be values. So how can we use the sort of feature stuff that we learned in the machine learning stuff to make this work for larger state spaces? Okay. So the slide has built this part first, which is great. So this is I can give you a preview. This is going to allow us to compress value functions for chess down to a small number of maybe 30 weights. Chess, there are 10 to the 43 states. So hopefully this should convince you that you should look at this math. We can now express V and Q approximately as weighted combinations of these features. The same thing that we did in the machine learning stuff. We have some weights. There's a vector of weights. We have a vector of features. We take a dot product of these things. Maybe that gives us our value function, right? Maybe it gives us our Q function. So if we have features of S, that could give us a value function. If we have features that take as input S's and A's, that could give us a Q value function. And this will allow us to sum up our experience with just a few very powerful numbers. The disadvantage is that states may share features but have very different expected utility. Okay, so we have a linear value function. We have a set of features, and a linear combination of those features gives us our value function. How could we update it? We take our original Q-learning rule, right? This is saying update Q in the direction of this target. Well, instead, we're just going to update the weights to reduce this error. So we take our original weights and we move them in the direction that minimizes the error. So there's some delta here. This is saying the delta of Q with the weights. This is saying like the derivative of the Q function with respect to the weights. And if we just multiply this thing, that ends up being the features. So we're saying take the weights and add to those weights alpha times the current TD error times the features. And this will allow us to update the weights. This is the algorithm that will do it for us. The intuitive interpretation is that we're saying adjust the weights of the active features. Right? So I'm in a state, I see that I'm close to some ghosts. Right? If something bad happens, blame the features that we saw. Decrease the value of states with those features. States where I'm close to ghosts, decrease the value of the states that have those features. And if something good happens, like I eat a dot, increase the value of states that have features like that, close to a dot, right? So I want to be close to these dots. I want to be far from those ghosts. And so we can increase or decrease these features, or increase or decrease the weights of these active features, and that will help us to predict value better. And now we're generalizing across states that have similar features. Okay. So here's an example with Pac-Man. Imagine that our Q function says we have a weight of 4 on this function that there's a dot. Let's say that there's a dot north of us, right? And we have -1 for there being a ghost if we want to take the action north, right? So we're in this state and we have this function that says, if I think about going north, is there a dot? Is there a ghost? And what's the importance of these two various features, right? So the action is north. We run our agent through a transition in the environment, and we see that the reward is -500. That's a pretty large negative reward. Here's our next state. We died. Oh no. Right? So the Q value of that S prime is 0. It's terminal. We're end of the episode. And so we say, okay, well, the Q value of the state we started in and going north, maybe it was +1 to start. Our target is R plus gamma times the max of the Q values. Well, R is this -500, and then there is no sort of next state because it's a terminal state. So we say -500. Now we have our difference. It's -501. It's a large difference. So we're going to update the features. We're going to say the weights. We're going to update the weights according to these features, right? These were the active features. And so we're saying we start with our weight 4, right? For this dot, the weight was 4. And then we're saying move that alpha times -501 times the feature being 0.5. And similarly for the ghost, this is saying when I see the dot, basically decrease the weight for the dot because the dot being there is bad. Is the dot always bad? No, but the fact that the dot is bad when the ghost is bad is what we're capturing here. So we also have to decrease the weight for the ghost. We have a -1. We're going to decrease that by alpha times -501. So we're decreasing the weight for the ghost being close to us by more than the weight for the dot being close to us. And so over time, this is going to say, okay, it's more important when I'm in a state like this that I see a ghost is nearby than I see a dot is nearby. So I should try to avoid the ghosts rather than going for the dot in a state like this, right? So these are the resulting QSAs. But this depends on the learning rate. Okay, so we can actually do this approximate Q learning with our Pac-Man environment. And what we'll see is, okay, we'll run it, and Pac-Man's going to learn very quickly from experience that dots are good, ghosts are bad. Oh, okay, so let's do it. So Pac-Man's going to run through the maze. Okay, dots are good, ghosts are bad. Okay, dots are good, ghosts are bad. Okay, dots are good, Dots are good. Dots are good. Dots are good. Ghosts are bad. All right. So what is that? 3 episodes? Like, what quick learning is this? This is amazing. So yeah, so approximate Q-learning, this idea of approximating functions, is like really powerful. It allows us to generalize very quickly as long as we pick the right features. Okay? So these are the approaches to reinforcement learning that I sort of listed for you. We've talked about model-based, learn the model, solve it, do the classic MDP thing, get your policy. We talked about learning values from experiences and using values to make decisions. First, there was direct evaluation. One note is that this is also sometimes called Monte Carlo evaluation, because we haven't used that word enough in this class yet. So Monte Carlo evaluation. So the direct evaluation, basically we generate a bunch of experiences. Any experiences that match the particular state we're estimating value for, we'll try and average those together. But we can't reuse samples the way we can with TD learning. TD learning is a way of then estimating the value of a policy, similar to policy evaluation. And then Q-learning we just talked about. There is this last piece that I wanted to just touch on briefly, which is to optimize the policy directly. This is called policy search. And today's code is dopamine, because I just think that dopamine thing is very cool. So the idea with policy search is, let's start with a policy. It doesn't have to be a good policy. But we know how to optimize things, right? We did our whole unit on hill climbing. We've learned about gradient ascent. There's lots of things that we can do to optimize now. So what if we just take our policy and try to make small updates to the policy that improve some objective function? Objective function like expected discounted reward. Right? So the problem is that sometimes these feature-based policies, the ones that work well aren't the ones that approximate the value function the best. So it can be the case that like this feature stuff works well, but it doesn't work well in the way that we're using it. I'll skip through some of this stuff for time. So basically the solution is we want to learn policies that maximize rewards, not necessarily the values that predict those rewards. So the approach with policy search is that we're going to start with an okay solution. It could even be a bad solution. And then we're going to fine-tune it by either hill climbing or gradient ascent in order to try to converge on a policy that achieves more reward. So we have to come up with some objective function. And usually our objective function will be something like the value of the starting state. But it's a very simple idea. We're going to start with like a linear value function or Q function. We could start with any policy. And then we're going to nudge the feature weights up and down and see if the policy is better than it was before. So we start with some policy. It has like some parameters in it. This is like, what's the probability of taking that action in that state? And then we're going to just like make small changes. Or we're going to say, in state 10, I'm now going to go up all the time instead of going left all the time. And we're going to see, does that lead to better initial state value, or does it lead to worse initial state value? Then we can do the hill climbing thing, or we can do gradient ascent if we want. And this will actually work really well for partial observable problems where we have partial information about the world. And it will allow us to optimize stochastic policies, which tend to be the ones that work best for these partially observable environments. There's a few cons, which like, how do we tell that the policy got better? I just said, here's our evaluation metric. It's the value of the starting state. But, checking if the policy got better means we have to run a whole episode. That could require a lot of experiences in the environment. We also may need to sample many episodes to make sure that we get a good estimate. So if there's lots of features, this can be impractical. There's like some caveats to all this. But policy search is like a very powerful class of methods that it would be a shame if we didn't have time to touch on. And here's an example with a helicopter from Andrew Ng's project at Stanford. And what's cool about this is that they're training this helicopter to fly with policy search. And that's not even the most exciting piece about this. It's flying upside down. Okay, so they initialized it and then fine-tuned it with policy search, and it can now fly upside down, and they'll zoom in a second to prove that to you. It's flying upside down, this helicopter. So you can do quite a lot with policy search, and some of the sort of like state-of-the-art reinforcement learning systems these days are using various versions of policy search. So that's the big picture here. I will say that RL, in summary, it solves MDPs via these direct experiences of transitions and rewards. We no longer have to have a model in advance. There's several different approaches. We can learn the model directly and then solve it. We can learn a value function from sums of rewards or by these local TD adjustments. If we do that with TD, we still need a model to make decisions by look-ahead, but we can use a Q function instead of a V function, and then we can just directly pick actions with an argmax. Or we can optimize the policy directly, whatever sort of works best for your problem. And when the problems get too big, we can scale that up with feature representations and approximation. Okay. That's all I have. Questions on this? Yeah, question.
Is there a way for us to like systematically get the features, or is that something that we still have to figure out on our own?
Yeah, that's a good question. So when you are optimizing for, let's say that we look at like this Atari example, right? So we have an agent that's playing Atari. We can build a neural network that is going to do the Q value approximation for us. And you can give that neural network model various features. Or we can just give it pixels. And the neural network can figure out what the features are supposed to be on the inside. So if we have like a big neural network, we can have it learn the features for us in the process of doing a good job of estimating these Q values. So we have all the pieces that we need, right? We talked about neural networks, we talked about function approximation. Basically, you put all these pieces together, and that will help you to learn the features. They'll be somewhere inside your neural network. It'll be a little hard to inspect. And this notion of like interpretable machine learning is definitely sort of like a hot topic these days. Like, how do you know when you have this big collection of weights in a neural network that like anything useful is happening in there apart from like the high level behavior? Like, what's going on? Why is it making these decisions? So interpretability is going to be a challenge, but you don't have to learn the features anymore. So yeah, it's a bit of a trade-off. Is that a okay, satisfying answer? Okay, nice. Other questions? Okay, then we'll see you next week.